Hello, good morning or afternoon. We are doing geometry, and today we're going to be going over triangle congruence. Triangle congruence. That's where we take a look at two triangles and see if each corresponding angle is the same and each corresponding side is the same length. Right? We want triangles that have the exact same shape, the exact same size. Those are congruent. So let's do this warm up. Let's take a look. We have I'm giving a little directions here, some notes. Two triangles will be congruent if they have the same size and shape. Two triangles will be congruent if they have the same size and the same shape. We can now say, given our studies of rigid motions, that two triangles in the plane are congruent if a sequence of rigid motions can be found that makes the vertices of one triangle coincide with the vertices of the other or lie on top of each other. So this idea is that if we can take these two triangles and through rigid motions, like a reflection, I can make this one pop on top of that one perfectly, and those are two congruent triangles. I'm going to cough. I've got to press pause. All right, saved you from that cough. Exercise 1 in the diagram below, and these are set up just like Regents' questions. In the diagram below, we know the following. So there's some assumptions. Given, that means assume, that ADC is a straight line. So ADC, we're going to assume that's a straight line. That's what it means to have a straight line on top of it. It says that's a line segment, like we learned about on the first day or two of geometry. Then it says here that line segment BD, so BD, line segment, is this symbol here means perpendicular. It's like an upside down capital T. It means perpendicular. That means they land at a 90-degree angle, a right angle. 90 degrees right there. That's what that symbol is. 90 degrees perpendicular. All right? So BD is perpendicular to AC, which means BD, this little line segment right here, is perpendicular to this one here. What we can do is we can say that is 90 degrees. Because we have, that tells us right there that it's perpendicular. Therefore, it's 90 degrees. All right. Just checking out my camera for a second here. All right. And we also know that AD is congruent to CD. You see that's the congruent symbol. It's that equal sign with a little squiggly on top. It means congruent. AD, this right here, AD, is congruent to CD. This right here. So I'm going to make a little mark on my diagram, one little hash mark. Though that hash mark here and that hash mark here helps me remember that AD is the same length as CD. These two are congruent. They're the same length. What the Regents and what this question asks you to do is prove that triangle BDC, prove that this guy, this triangle, is congruent to BDA. All right? And based on the givens of the diagram, which rigid motion do you think would be used to map triangle BDC onto triangle BDA? Try the transformations with tracing paper. So let me hand out some tracing paper right now, and let's see if you can find a transformation that will map the one triangle on the other. And then prove with rigid motions. So you're going to write down that you could write it, your answer is going to be something like either a translation. You're going to say translate the triangle ADC, translate triangle ADC, or maybe you're going to say rotate triangle ADC, and you're going to tell me what kind of rotation, whether it's 90, 180, or you'll say reflect triangle ADC, and that's all we're doing right now is translations, rotations, and reflections are three rigid motions. All right, so pause the video here, see what you can get me. I want to see if you can determine what rigid motion maps BDC onto BDA. All right, go. All right, so what your little video correction, what you're going to do is you're going to choose which of the three rigid motions will give us mapping triangle BDC, onto BDA. So this triangle on that triangle, show me either translating the triangle, rotating the triangle, reflecting the triangle. You tell me how that's going to work. Pause the video. See what your ideas you can come up with. All right. Well, I'm going to let you, we're either going to go over it in class or you can figure it out on your own. I don't think we need to go over that. Let's move on. Let's move on to the exploration part of this thing. Hopefully all the classroom necessaries have been completed by now. All the attendance and passes and all that kind of stuff that happens administratively. Exercise 2, in diagram below, we know the following. Given line segment ACD, let's find that. ACD, okay, this line segment here. And line segment BCE, that line segment there, with C being the midpoint of both AD and BE. So AD, that's this here, and BE. So C is the midpoint of these two pieces, of both these line segments. So right now, what is a midpoint? Pause the video, let's get some ideas. Midpoint, what is it? I think we talked about this at least once. All right, unpausing the video. Midpoint. Midpoint means the point in the middle. It cuts it in half. Good on you for those who guessed that. And if you didn't guess it, don't worry. That's why we're here. We're here to learn. We're learning new stuff every day. Guess what? You just learned something new. That's a good thing. All right, so what am I doing? I'm making one hash mark. In fact, that was kind of messy, wasn't it? I'm going to make one hash mark over here. I'm going to make one hash mark over here. That means that this piece is congruent to that piece. Okay? I'm putting two hash marks over here and two hash marks over here. Because while I know that these two are going to be congruent to each other, because C is the midpoint, right? C cuts it in half. C is that middle point. I don't know that CE is going to be the same length as CD. These look like they're going to be different lengths. CD looks longer to me than CE. So I can't do one hash mark on this one too. I have to do two hash marks to remind myself that this is a different length. I don't know what it is yet. It might be the same, but in this case, I'm looking visually. It doesn't look like it's going to be the same. All right. So we've taken care of the given. Here's what we need to prove, that triangle ABC is congruent to triangle DEC. So I want to prove that this triangle is congruent to that triangle. What rigid motion do you think you could use to prove that the triangle ABC is congruent to triangle DEC? Pause the video. Let's get some ideas. All right, unpausing the video. Well, I'm hoping you see that this is a point reflection. We went over the point reflection just yesterday, so if you didn't catch that, that's okay. Let me think. Could you also say if it's a rotation? Yeah, you could, couldn't you? Couldn't you see that? Couldn't you see this getting rotated around 180 degrees, flipped right upside down? So either way, you're right. Either way, 180-degree rotation, absolutely correct. Point reflection, absolutely correct. Let me show you how it's a point reflection. C is my point of reflection. A gets reflected beyond C, becomes D. B gets reflected past C to be an equal distance to E. So there I have my new triangle reflected past point C. So either one, you could write down point reflection on C. You could say, yeah, let's write it out to show you the symbols, how we do the notation. Triangle ABC is reflected on point C to map on triangle DEC. Or you could say, let me see, triangle, oop, that's not a triangle. Triangle, that's an A. BC is rotated 180 degrees to map, to overlap, to go over top of, to map on top of triangle DEC. Either one of those work. That's the English. Bonus points for anyone who can remember the geometric notation we learned yesterday. Anyone got that? It's a little bit faster to write it this way, but it requires a little bit more know-how too. Triangle A. Struggling with my ABC there. Let's see. Reflected. I'm going to reflect lowercase r on point C, triangle ABC. So that's my one notation. Reflect on point C, triangle ABC. Rotation, capital R, rotate 180 degrees on point C, triangle ABC. So I'm going to rotate 180 degrees on point C, ABC. All right, there we go. We got all this. Let's move on. Exercise 3. All right. We're going to complete exercise 3, have one more, and then we'll do the check for understanding. And we're only 11 minutes in. We'll probably get done early today. All right, exercise 3. In the following diagram, it is known that AB, so AB here, AB, bisects. What does bisect mean? It means to cut something in half. And in this case, we're going to bisect an angle, which means cutting an angle in half. Let me show you how that works. It is known that AB, right here, bisects both CAD, CAD, so this gets bisected, and CBD, CBD, this gets bisected. I'm going to give this 2 arcs to let myself remember that this is one angle measure, and then the one arc is another angle measure, and I'm going to remember that this is going to be congruent to that because it's bisected, and this piece is going to be congruent to that piece because it's bisected. All right. So this will be enough using rigid motion to show that triangle ABC is congruent to triangle ADB. All right. So what is it? What rigid motion do you think? Anyone calling this out? A rigid motion that'll map ACB onto ADB? Anyone? Pause the video. Unpausing video. A reflection. Do we see that? A reflection, a mirror image. This AB becomes the mirror. And then boop, it just flips back on top of there. All right. Use your tracing paper to confirm that if you're not sure, if you're not quite sure if you get that piece. Let's answer these questions. What angle pairs must be congruent based on what is known? So what angle pairs? This has to be congruent to that, right? If it's bisected by this, if this bisects the whole big thing, that means it cuts both pieces in half, which means the 2 halves are equal. If triangle ADB was reflected on AB, what 2 points would not move? So if I reflect ADB on this line, what 2 points don't move? Any thoughts? Well, the 2 points that don't move are A and B because they're already on the line. They're not going anywhere. You can't reflect them anywhere if they're on the line already. D is going to move all the way over to C, of course. But A and B, they don't move because they're on the line that we're reflecting from. If triangle ADB was reflected in AB, why must the image of point D prime, fall on both rays AC and BC? So if the triangle ADB is reflected on AB, why must the image of point D, right here, fall on both rays AC and BC? Well, the reason why it's going to fall on both rays is because this is going to be congruent to that, right? This is congruent to that when this is congruent to that. And I'm going to show you why in the future. There's a handy little theorem that we've already you haven't learned yet. But we're going to learn this one. It's called angle side angle. AB is congruent to itself. So for both triangles share AB. See how both triangles have AB in common? And AB is going to be equal to itself. Does that make sense? Something is always equal to itself. It is what it is, right? It is what it is. And we're told that these angles are bisected on both sides, so I know this is congruent. So in this triangle, I know that this angle, this side, and this angle is congruent to this angle, this side, and this angle. And if I have that much information about a triangle, I can say angle, side, angle, and I know it to be true. And then if I know the two triangles are congruent, then I know the legs, all the vertices are congruent, which means I know that this is equal to that, which means I can map it. All right, give me the smiley face if what I said made sense. Give me a happy smiley face. Give me the sad smiley face if what I just said didn't make any sense. And I need to think about how to break it down even more. All right. Let's go on to D. Since D prime, the new image after D gets projected over there, must fall on AC and BC, where does this tell you that it must lie? Okay. Well, hopefully, if we take our tracing paper, you can see it. Trace the triangle, flip it over, notice that D falls right back on top of C. Where does it tell you it must lie? It must lie on C. You explain because it maps right onto C. It's the two triangles are congruent, right? And explain why we know that triangle ACB is congruent to ADB. And for this to explain, it's because we can reflect triangle ACB onto, oh, actually, no, not onto. I can reflect triangle ACB over line, that was a terrible line, over line A, B, and map it on triangle A, D, B. All right. So that's this page. Maybe I should be filling more things out on the paper. I was saying things out loud without writing them down. But some of this is good. Some of it's good to practice listening and not just copying what we can visually see. Sometimes tracking the narration is also good. Helps us follow along and pay attention. All right, this one I will write down more stuff for those note takers in the audience. And you guys are great note takers. I'm very impressed by your note taking skills, which can come in real handy in a lot of times. Yeah. In diagram shown, the following is known: AB bisects angle CBD. This is angle CBD. So let me find that. Angle CBD. That's the angle that's getting bisected, and it's AB which is doing the bisecting. So AB bisects this angle here, which means this is going to end up being the same as this right here. These two things are going to be congruent because AB cuts the whole angle in half, right? And when you cut something in half, you get two equal halves. All right? Prove that ABD, triangle ABD, prove that this triangle here is congruent to ACB, using rigid motion reasoning. Okay. So first step, explain why we know that angle M, so the measure, this is that M in italics says the measure of angle CBA is congruent to angle DBA. Okay, we know because if AB bisects angle CBD, then it cuts it into two equal parts. If AB bisects angle CBD, then the bisector cuts it into two equal parts. That's what bisecting means. Bisecting means cutting things into two equal parts. So we're told it bisects, which means we know these two things are equal. We get two equal halves because it's bisecting. All right. Now we don't know that CAB and DAB are correct. So we don't know that CAB are congruent and DAB is congruent. We don't know that yet. A reflection of triangle ABD across AB leaves what points unmoved? Again, the points that are unmoved when I reflect this triangle over this line are all the points that are on the line. The points on the line don't move on a reflection. They just stay where they were. So A and B stay. I'm going to cough, got to press pause. A and B stay because they are already on the line. Already on the line. The image D under reflection of AB must fall on C. This needs both measure of angle CBA to be equal to the measure of DBA, and BD has to equal BC. So this is going to be congruent to that. So explain why we need to know, why does this side and this side, if we don't know that the two angles, if I don't know that this is congruent to that, in this case I don't know that these two are congruent. What I'm told is that this is congruent to that, and I'm told that BD is congruent to BC. BD is going to be congruent to BC. So what I have is, I know that this side is congruent to this side for both triangles. I have an angle and I have a side. Why do I need to know that this side? Why couldn't I just have this side here and then the angle? Why wouldn't that be enough? Pause the video. Let's see if we can get some ideas about why the triangles might not be congruent unless I know for sure that these two pieces are congruent, that BD and BC are congruent. Pause it here. All right, unpausing. I need to know that both of these are congruent to be sure that these triangles are congruent, because what if BC is just a little bit longer? If BC is just a little bit longer, then this angle measure changes. If D is actually a little bit longer, and this angle here might still be the same, and then these two angles might be congruent to each other still, and this side might be congruent to itself still, but unless these two sides are the same, I could move this point out, I'd get a different angle measure here, and these triangles would not be congruent, right? If this was anywhere, if this piece here was longer than that piece, then these two triangles would not line up. Their angles would be changing. So it has to be the same, because otherwise the angle measures would change. Because if BD was not congruent with CB, then these triangles would not be congruent. Then the triangles would not be congruent. All right, there we are. So we can pause the video here for those who want to catch up on those notes. I wrote them on this page. Again, I do want to inspire some independence. I want to make sure we keep listening. And And it's okay if you have some blanks in there, you missed it. If you're watching the video, you can watch the video over again, get those answers on the previous page. I said them out loud. I'm going to flip the page over here. Already the check for understanding, 25 minutes into the video. I'm going to cough. All right, check for understanding time. I'm going to have you guys do most of this check for understanding yourself. I'm going to explain the directions, but I really want you to fill it in. I don't want to talk about it too much. I want to make sure that you can do this on your own. This is important. Independence is important. We need to develop our own risk-taking and our thinking. Now, you can work with a partner on this. No problem whatsoever. Work with anybody in the class, but I still want to give the answers away. I want you to struggle a little bit. I want it to feel a little uncomfortable, because in that bit of uncomfortable stress, some learning can happen, okay? In the following diagram, triangle ABC, ABC, and triangle ADC are drawn with a shared side AC. So this is a shared side. This triangle here and this triangle here are drawn with a shared side. That's their shared side right there. So it's the big triangle it's talking about. We are given the following information, all right? AB is congruent to AD. So let's mark that on. As soon as you see that as a given on a Regents test or anything else, mark that on your mark that on your diagram. AB is congruent to AD. We also know that CB is congruent to CD. CB, I'm going to mark 2 hash marks because obviously that's not going to be the same length. It's going to be congruent to CD. So this is congruent to that. My first part is that point A is equidistant from points B and D. A is the same distance from B and D. Well, we kind of already knew that, right? Didn't we? It says A is equidistant from B and D, and the reason why we already knew that is because we already know that these legs are congruent. If these legs are congruent and the distances are congruent, which means we knew that A was equidistant from B and D. So point C, so is point C. Point C is also equidistant from D and B. And again, we knew that prior because this is congruent to that, which means the same distance, which means this distance from C to D is the same distance to C and B. This means that AC has a special relationship to segment BD. Explain. So what if this is the same distance as this, and that's the same distance as that? What do you think it means for this? What does that mean for that? You do this in blue for BD. What is the significance? What do you think it is? Make a guess. Be wrong. Take a risk. You might be right. It's okay if you're not. It really is. Just try. Guess. Think. What does it mean that they're equidistant? What effect would that have? Pause the video here if we need more time. Unpausing the video. If we reflect the triangle ABC across AC, if we reflect ABC across AC, all right, I'm going to reflect it over. Looks to me like it's going to map right on top of there. What points stay fixed? We asked this question before. What points stay fixed on a line reflection? You tell me. Write that down. Pause the video if we need more time. Unpausing. Why must point B fall on D? Why would this fall on this after a reflection over AC? You're going to say something like about it being the same distance, it being a line reflection, it mapping onto one thing or the other. Use our terms here. Pause if needed. Unpausing. D here. Why does a reflection of triangle ABC in AC show that ABC is congruent to ADC? Why would a reflection of ABC over the line AC. So why is it that if I reflect this triangle here over that line, why does that prove that the two triangles are congruent? You should say something about congruency and rigid motions. Congruency and rigid motions. That's what we're all about today. The learning target was that you could determine triangle congruence through a series of rigid motions. And then after you're done with that question, give me that reflection. Tell me how today was. We're wrapping up early. That's good news, right? What's working in the classroom with your learning or with the instruction? Maybe you could give me some feedback on the reflection question and propose a better reflection question. I've been rethinking my reflection question and refining it over time. So do that reflection. Pause the video if you need time here. Let's look at the homework. All right, the homework says reflect ABC. So there's ABC right there. Reflect ABC across BA. So reflect it across this line here. And then translate ABC so that A goes to D. All right, so here I go. I'm reflecting. When I reflect on a line, these two are going to stay right where they are, right? A and B is already on line AB. Therefore, they stay the same. The only one I need to reflect is point C. Point C is 1, 2, 3 points away from this line. So it has to go 1, 2, 3 points right there. So my new triangle is going to be right there. If you can see that. There's my reflection of my new triangle after reflected on AB. And then I need to translate my new triangle, A prime, B prime, C prime, so that A goes to D, so that A lands on D of this new triangle. So a translation. What do I need to do? I need to translate. I'm going to go, what am I going to call this? I need to go to the right. How many units? 1, 2, 3, 4. So I need to go 4. I need to increase my x value by 4. I need to go down 1, so I'm negative 1. So T, I'm going to write a capital T, parentheses, 4. That 4 says I'm going to increase my x value by 4, bring it to the right 4, comma, negative 1. That negative 1 in the y value says bring it down 1. So now this triangle gets brought down this much, then there, and then all these points get brought down that much in there too, mapping the one triangle on the other. Give me the smiley face reflection on how that just felt just now. How did that go for you? This one here says rotate ABC clockwise 180 degrees about point B. So we're going to rotate it right on point B there. And then translate ABC so that B goes on E. So all right. So I need to rotate 180 degrees. What happens? Well, B stays right where it wants to be if I'm rotating 180 degrees. C is going to go, I need to go down 3 over 1. So I go down 3 over 1. There is my, hold on, I'm going to cough. This is my 180 degree rotation of C over B. There's C prime. And A is actually, I did not do this. I should not have done this way. But there, A is 1, 2, 3 units from B. Do you see that? Which means I need to be 1, 2, 3 units. Oh, Mr. Solt, you made this thing go off the grid. Yeah, I know. I goofed. Sorry. It happens. As they say from Steinbeck, the best laid plans of mice and men. All right, there's my triangle, rotated 180 degrees, and around point B. And then I want you to translate ABC so that B goes on E. Well, I can translate B on E, but when I translate B on E, I'm not going to get this triangle to map. But that's okay. I'm not going to get it to map. So to translate B to E, I need to go down 1. I need to go over 1, 2, 3, 4. Oh, it's the same one. So translate t. Let's see, I need to go to the right 4. So x is going to be added 4, down 1. So it's the same translation as we saw last time. Over 4, down 1. 1, 2, 3, 4, down 1. All right, there it is. Somehow I feel like I did not compose that question well. I wanted these all to like line up, and I think I goofed this one up somehow when I drew this one up. Anyway, reflect a triangle ABC across BC. So we're going to reflect it across BC, this line right here. And then translate ABC so that B goes on E. So there's E right there. So I want to get this over. So to translate, these all stay the same. These 2 points here stay the same because they're already on the line. So the only thing I need to translate, or sorry, the only thing I need to reflect is A. A is 1, 2, 3 away. So A is going to end up being, let's see, it's going to end up, it has to be perpendicular. So it's going to be here. And why do I say there? I can understand if you're confused right about that. Why I decided it had to be right about there. In fact, I'm not quite on it. How did I? More like there. That's better. When you reflect across a line, it's got to be perpendicular. So what I have to envision, how many do I have to go down and over to get to the same spot that I was? So I went over 3, went to the left 3, down 1 to cross this line. So I need to go left 3, down 1 to get over it. And again, I went off the grid that I had scheduled there. I went off the grid. But yeah, so my new point should be somewhere right around here, which means my new triangle will be right here. This is my new triangle. And yes, I can map a point on a point, but this triangle is not going to map perfectly on top of this one because it's not rotated the right way. It's not in the right orientation, but I can map B on E. So B is right here. How do I go from B to E? Let's count. To the right 1, 2, 3, 4. Oh no, another fourth one. Yeah, I did it 3 times. 1, 2, 3, 4. All right, and then down 1. So I'm sorry, this was kind of boring. I must have had 4, -1 on the brain when I put that together on GeoGebra. Okay, that's the homework. All right, we've hopefully by now you can say that using some rigid motions you can determine if 2 triangles are congruent. So yay you got something learned. Fantastic. Let's find out what we're going to learn out tomorrow. Have a good day.